an LED power supply from China. It's a while since I've taken one of them to bits, and I bought this one because it had a particularly unique feature. The listing says DC 12V LED outdoor rainproof power supply, 660 watt, 100, 200, 250 and 400 watt LED driver, and it looks as though they're designed to mount on a wall or tree or whatever, and then they do seem to have the facility to shed the water. And it also says helpful things like LED rainproof power supply, shows it on the wall, high voltage, non-professional, do not open it. Please cut off the power when you open the cover, should be installed vertically, do not invert or horizontal. And then it showed pictures of the bottom. You're thinking, well, that doesn't look very well sealed, does it? Let's open one and take a look. So when you take the unit out initially, it looks pretty good in the sense that it does have this plastic shroud on the top that will effectively shed water over the unit and stop it going in. But the bottom is completely open. There's no restraint relief. Those are effectively live connections in there, so it's not quite as waterproof as they're implying. Also, if you look inside, it's got this little lid that flips up. If you look inside, it's a switchboard power supply, but there's big voids in here that insects like spiders or anything that wanted a nice warm home could get up in there. And anybody who has dealt with insects and switchboard power supplies, it's usually quite apocalyptic. So I think we should open this up and take a look. So I'm going to use these screwdrivers since let's use, not sure which size it's going to be, but it's Phillips screws. Let's use the VDE rated drivers. I don't know if that's actually going to fit up there. No, it's not going to fit up the hole up there. Okay, that's okay. Let's just whip everything off. So it's the usual construction. The plastic end cap is going into the end of an extrusion. I haven't tested the power rating. There's a couple of things you should be aware of if buying power supplies from China. One is that their electrical standards aren't quite up to the same standard as ours, and therefore the isolation between the main side and the low voltage side may not be quite what you want. It does carry that risk of stuff coming live. And the other thing you should know is that they tend to over-exaggerate their ratings somewhat, so this one is actually supposedly 100 watt rated. I'd probably only use it to about half that if I was going to use this. What's this going to reveal? Oh, blimey, it's revealing a big void. Okay, the circuit board's well down in there. Let's take this end off. Going to have to use the other screwdriver bit for that. It's a shame. I was kind of hoping it might actually have had some sort of like water shedding system, you know, vent holes to let it vent, basically, to let it breathe. That always really helps with electronics like this. But some sort of cable restraint and finger guard would have been quite nice. It would have finished this off nicely, and in a way they could have made a longer plastic section and actually incorporated that. You don't want to seal it up completely because that's not usually a good result. It just traps moisture inside. Oh, this has actually got a... Oh, it's got a cover that slides off. Okay, things I'm spotting immediately. I'm spotting the incoming supply. I'm spotting an NDC inrush thermistor. Tell you what, I'm going to whip this circuit board out and get some information on it. I'll take some pictures and then we'll take a much closer look at it. The power supply has been reverse engineered. No major surprises. It's a very straightforward design. Let's start with the power supply coming in. I've flipped this, by the way. The reason all this text is the wrong way around is because I've flipped it over, and so you can actually relate the component positions to the track positions, which are the correct way around. The supply comes in here. The earth is not connected to anything. It's just floating earth. It's just a token gesture earth terminal. It would have been nice when we connect to the case, but there's no attempt at all to do that. I suppose they could have soldered a wire onto that and run it to a little crimp or something and then screwed it onto the case, but they didn't. We have the live and neutral coming in, and the neutral has kind of a fuse in it. It's got the little track here that's designed to blow, but it's also got a couple of solder pads. I wonder if that's to repair it if the track does blow for some reason. Not sure. It then goes through this black component here, which is an NTC thermistor. NTC, what that does is it limits the inrush current. An NDC resistor starts off with a slightly higher resistance. It doesn't actually start with a very high resistance. In this case, well, let's measure it. Let's measure it right now. Let's put it to 200 ohms because I'm not expecting an awful high resistance. Where is it? It's there, and we shall measure across it. So I want to go there and there. It's about 6 ohms minus the sort of lead resistance. Let's say 5 or 6 ohms. It's really not that much, but it makes a difference. When you first turn a power supply on, this capacitor is discharged, so initially the current will want to charge that up and it will effectively short out the supply briefly. And if you've got a lot of these power supplies in one circuit, the potential for an inrush current could be enough to actually cause the circuit breaker to trip out magnetically instantly. So this starts off with a slightly higher resistance, about 5 ohms, as I say, not much, but then as this warms up, because it will dissipate a bit of heat across it because of its resistance, it then goes down in resistance, and it just wavers up and down. It will stay warm in operation. It's just how they work. After that is the bridge rectifier. The bridge rectifier, the full bridge rectifier. Full bridge rectifier to, quote, electro boom. And then after that is a big fat capacitor here. And that is basically the DC supply for the circuitry. The circuitry itself, instead of using a chip to switch the transformer directly, it uses this tiny little 6-pin chip. And it had the code PR65 on it. I couldn't find PR65, but I did find an equivalent chip by Semi. And it drives a big chunky MOSFET here, which means that, ultimately you can scale this circuit up depending on the power required. I shall bring in the Semi schematic. That's a good call here. Let's nudge up just a tiny bit. So here's the incoming supply. We've got on the neutral, we've got that NTC and the sort of fuse. We've not got an EMI filter. There is a very, very vague nudge in that direction. With this component here, there's a position for a little capacitor. It's just token gesture. It goes through the bridge rectifier, and there's the big capacitor, 33 microfarad, 400 volts. Now, when you're running these little transformers, it would be nice if you could just use it like a standard power supply and stick 240 volts AC across that transformer at 50 or 60 hertz or 120 volts or whatever your local supply voltage is. But in reality, you can't do that with the small transformers because they've got a very low winding impedance. They've got a very low... They wouldn't have much current throughput at that. You can get transformers this size that run directly on the 50 or 60 hertz, but they're not very... They're only rated about, say, 1 watt, 1 volt amp. So to actually make it more efficient, to allow the use of a smaller transformer for higher current, to save the weight of metal and save weight, metal, and I suppose costs it comes down to in the long run, what they do is they apply a DC supply to this but pulse it on and off. So they effectively run this little transformer at much higher frequency, and that allows it to put through much higher power. So it just makes things more efficient. So the circuitry is very straightforward. It's very typical of these type of chips. It's a clever little chip. It has the transformer here. Let's draw the windings on, in fact. The secondary winding is just a beast. It's got like 3 common sets of pads here, and it's just a very common group of ultimately it's like 3 strands but all twisted together and just run round the transformer just to make it easier to actually wind. And also it must probably has some other magnetic advantages as well. The primary appears to be the positive going to the MOSFET, so that's the primary, and then there's another little winding here which is used as a bootstrap. It's used to power the chip, and it's very classic the way it does that. Initially I thought, with these tiny chips, the pins are so close together, doesn't that pose a slight risk of problems with the voltages involved across it? But it turns out that this chip at the max has about 30 volts across it. I think I had the specification for that here. Have I got the specification? It's not going to tell me on this page. That doesn't matter. So the equivalent chip, incidentally, is the WS2293. It's got the same pin out. I'm not sure. I'm guessing that this is just a standard format that all the manufacturers copy so that, they can provide a pin-for-pin replacement. But it turns out this has quite a low voltage across it. In fact, it shunts. It's got a shunt inside it that when the voltage goes above about, say, 30 volts, it'll shunt that down. It also has an internal shunt for the MOSFET, so it doesn't drive the MOSFET gate above about 12 or so volts. So the transformer, the chip drives the MOSFET. It does so via a 22 ohm resistor. That's that tiny little 22 ohm resistor there. And there's a link across here. There's also, the one difference in this design is it's got a diode, presumably to help it turn the MOSFET off faster by discharging it. I'm not sure why. It's the only logical thing I can put to that. So the current flows through this MOSFET when it's running, and it senses how much current by this sense resistor. In reality, that sense resistor is 1, 2, hold on, no, that's wrong. It's 1, 2, 3, 4, 1.2 ohm resistors in parallel, giving a combined resistance of 0.3 ohms. And as soon as it knows how much current's flowing through, because as soon as it reaches a specific voltage threshold, it knows it's reached that current, and it will turn the MOSFET off. There is a snubber network, as there usually is, across this. This is the primary winding here, P. We'll call that bootstrap, we'll call that secondary. There is a little snubber network to protect the MOSFET, because when the MOSFET turns off, there is potentially a sort of voltage spike, and to protect that, they've got a capacitor here, which is this capacitor. They've got a diode here, which is this diode. And then they've got 3940s, 390k, let's say 400k, 4 of them parallel, giving about 100k, but they've used 4 in parallel, just like there, just to spread the dissipation, to lower the heat dissipation of the chips. So that covers the snubber network. The power supply for the chip is derived from 2 sources. You've got these high value resistors, and those 2 resistors here, the 754, that's 7540, 750k, 2 of them in series is about 1.5 megohm. So they've effectively got 1.5 megohm. And when you turn the chip on, the first thing that will happen is that current will start flowing through those resistors and charging up this capacitor here, which is this little dinky capacitor over here. And when it's charged up to a high enough threshold voltage, the chip will boot up, and it will rely on the charge on that capacitor to initially keep it running. But it will drive the gate of the MOSFET. The MOSFET will turn on, it will put a magnetic field into the transformer, then it will turn off, and when it collapses, it doesn't just put the current over to the other side on the sort of other half of that waveform, but it also puts some current out this side, and that also lets it monitor. If you were to short the output of this, it would shunt that magnetic field so you wouldn't actually get anything out this side, and that's when you see that effect when the things are trying to power and it's just making tapping noises, or the output lights are blinking if something goes wrong with this. But when when the MOSFET turns off, it puts a small burst of current through this diode, which is this diode here. And then there's a resistor, which is there a resistor? Yes, there is. This is that wind there. So it goes through this 1, 0, and 0. So a 0 multiplier, that's 10 ohm resistor. It goes, let's get that out of the way. It goes through this resistor, goes through the diode here, and charges up that capacitor there, and that's its power supply. So once it's initially booted, it will power itself from that auxiliary winding, and it can also monitor what's happening in case there's a fault condition. Anything else worth saying there? Right, the output. The secondary is shown here with a diode with this little mini snubber network. Maybe that's for noise suppression, not sure, and feeding that capacitor. In reality, what it's got here is it's using, I'm just shifting, everything is just like sliding about. It's using a double Schottky diode here that's rated, what's that rated? The diode is called a JFF M8N60C. No, that's the MOSFET I'm talking about there. The diode is a MBR20100FCT. It's rated 20 amps at 100 volts. And it actually contains 2 diodes, so you're effectively looking at an arrangement like this in here. Quite a common arrangement. By using that package, it's an efficient way to do it. It might actually just be 1 diode, but just common. I could only test that if I desoldered it, which I'm not going to do. But the equivalent on the schematic here is that other diode there. And likewise, they do have the little snubber network across it. They've got the 470, that's 47, and a 0 multiplier, so 47 ohms, but they've got two in parallel, giving 23.5 ohms, and they're in series the capacitor just to, I guess, suppress output noise. Then we've got a big fat capacitor here, big fat capacitor, and I shall mark that up as being, that's going to be the negative side, and that's going to be the positive side of that capacitor. And there's a 102, that's 1020 multiplier, so it's like a 1000 ohm resistor just across that. I'm guessing is that to provide an auxiliary load, just if there's no load at all, it will make the circuit more stable, or is it just so when you turn it off, the voltage doesn't linger too much? Because sometimes if the capacitor's discharging slowly, instead of the LEDs in the output just going out, they'll just gradually fade away and look a bit uneven. But there is also an LED here. The LED that is tucked down here, see the little green LED sneaked in there? So there's that LED, which is wired like that, and it's going through that 1K resistor to the other pole, so it lights. It's basically just a LED and resistor across the supply rails. Those, incidentally, are the output, the negative and positive output. The feedback is quite a complex circuit in this one here. It's using an opto-isolator, and this one is using an opto-isolator that's signalling over to the other side there. So when this LED lights in this opto-isolator, it means that the voltage is high enough in the output, and it will turn the unit off. It will go into standby until that LED goes off again, and it gets the signal to actually turn back on. But whereas it's quite a complex circuit here based around a voltage reference, probably a TL431 voltage reference, in this case they're not using that. They're using something very simple. They're really just aiming at a rough 12 volts. So they've got this Zener diode here, which is in this location here. And they've got a couple of resistors going from the positive rail. One is going to the opto-isolator, the other one is going to the opto-isolator and then the Zener. And the way that works is as soon as the voltage exceeds the forward voltage of the LED in the opto-isolator here, which is coupling incidentally, this is the opto-isolator here, and it exceeds the forward voltage of the opto-isolator and the Zener diode, and one of those resistors is just to provide a continuous current through that Zener diode, just to make it operate more stably. As soon as the Zener's exceeded and the forward voltage, it lights the LED, it fires the signal across, and on the other side, it's connected, and one of them connections is connected to negative. The other track goes up here, jumps across this wire link here over to here, and there's a little capacitor here to the negative rail to decouple it. Does it have that in the original? It does. That's that little capacitor there. That's the opto-isolator going there, and it goes into this pin here in the middle of that chip. There is another little resistor here, 100K, I measured the value at, R1. That's used to set the frequency of the device. It looks quite versatile. What else can I cover? I think that's me just covered it all. The component numbers, the MOSFET they've used is the JFF M8N60C, and it's rated 600 volts at 8 amps. It's just designed for switch mode type applications. And that more or less sums it up. A very basic, maybe a bit too basic power supply. It doesn't really have much in the way of noise suppression or filtering, like a typical, the equivalent power supply, if it was UK compliant, would be filling more of that case up. It would have like a COM mode suppression choke and filter capacitors here. It would be trying to get rid of that noise. It would also have a class Y capacitor somewhere between, see this green line? This is the separating line between the mains voltage side and the low voltage output side. But there would typically, probably in this vicinity here, you might find a capacitor that just bridged both sides to provide a route back for electrical noise from the main side that was coupled capacitively between the two windings. So what else is there to say about this? Separation. The output windings are not double insulated output windings. You get the thicker insulation version that has a much thicker coating on the wires. Do they call it triple insulated? I don't see that. And there is an attempt to sleeve some of the wires going in here, possibly where they go across the bottom of the bobbin, just to keep them away from those other connections. But from transformer to transformer, you just don't know what the separation is like in that. I think we're just ending up resigning ourselves to, the fact that there is minimal separation. And certainly, when you slide this into the case, this unearthed case, it slides in this little rail at the bottom that keeps the circuit board well away from the base here. Well, not if there's insects involved. But the spacing between, say for instance, that live track and the side, it's about 3mm, which, it's reasonable enough. And the top, they've actually got a line. You can see the line here and one here that represents where this case actually kicks in. And the metal will be in that vicinity, but that means it's just a couple of millimeters away from the MOSFET connections. So not, it would have been nice if the case had been earthed. It would be nice if lots of different things, if the transformer had triple insulation. It's just one of these things. This is why I say that if you've got a commercial application, I wouldn't recommend using any of these where the public might touch something, because there's no guarantee of electrical separation. At some point, this factory may put out a rogue unit that has 240 volts present on the 12 volt output, and the unit will just, because they're isolated, when that break of isolation happens just in one contact to the winding, it will still work. It will still put out 12 volts, but it will effectively be referenced to the main side. The case goes together with this slides into the housing here, and that more or less holds it in place, apart from when you slide this in, you've got these little metal tabs. And as you slide it in there, those tabs, you put a bit of heatsink compound on the transistors, then those lock against the transistors and the diode package, should I say. Ew, bit footery. I suppose if you're in the factory making lots of these, it's quite easy. And when they're tightened up, the shape of the metal is such that it cantilevers with a screw and it grips those onto the side. But that's pretty much all that holds the circuit board in place. It could theoretically slide back into the unit further, apart from the fact it's hitting the screws. But there's nothing, once you've got the cables attached, the only thing that's holding this in is the fact this is screwed up against the end and this is being pulled down hard against that plastic. It's interesting. The waterproofing is just not good enough, unfortunately. That's a shame. They could have gone that little bit further. They could have extended this plastic down and maybe put a couple of gland positions on it and then perforated it with lots of holes so that, it would still have that draining facility, but it would limit the size of insects that could get into it. I suppose this is ultimately why most of the real waterproof power supplies tend to be potted completely in that sort of silicon goop. Hold on, picture of one, which is not actually terribly flattering. Here's a picture of one in a tree in Glasgow. There's the completely potted power supply, but still designed to mount an enclosure, because instead of a flex coming out, it's actually got two single insulated wires, brown and blue, coming out the end, which is really odd that they did that. I guess it's just so they can poke it through the mould, but that's not really compliant with the regulations, having that up in a tree just single insulated. And then it's going down to this junction box, and there's a stuffing gland there, and the stuffing gland, the cable gland, isn't going to, it can close on those wires if you tightened it up far enough, but it's probably rated for natural flex. So the water's going to run down those, and this junction box that's literally hanging off those two wires is just going to fill up, and because it's waterproof, it will fill up to the brim, and well, there you go. But that's what the waterproof ones look like when they're being misused, apparently. Yeah, see if you can identify where that tree is. It's always quite interesting looking at other people's electrical work. And that's more or less it. It's neat enough, it's a functional little design. The separation isn't fantastic. There's no sort of routing out for anti-tracking. Certainly, I wouldn't rate this for a wet environment, even though that's what they rate it for. And it is just going to be a nice haven for insects. And when an insect, particularly in this area here, if an insect crawls over there and bridges with its legs, it could turn the MOSFET on and actually cause it to saturate the transformer. It would bypass everything, turn the MOSFET on and cause it to fail and make the whole thing go bang. So really, insects and electronics don't really mix that well. Neither does the HAR, which is a sea fog that comes in and just coats everything. If we had this mounted as they show it in the listing in Edinburgh somewhere on a wall, it would, when the HAR came in, water would just be dripping out the inside of this. So I don't know what their application is. I could imagine that maybe they might use them inside a sign, and it's just a little layer of extra protection in case water drips in it. I think that's all I'd really consider it for, inside a fully enclosed box sign, that where the metal case is earthed in its own right, and this is just an extra layer just to stop water dripping from above onto an open power supply. But it's smart enough. It's nicely assembled, even if it's not quite rated for how they actually expect it to be used.